Recording started.
Okay, good evening, everybody. Professor Ayorinde, welcoming you back from your examination week, right? So anyway, before we start the session today, a couple of announcements. I have finished grading your last exam, and of course the result has been posted in Blackboard. So I want you to stop me about 5 minutes to the end of our class today so I could give your exam papers back to you. And also the next online review session will be next Wednesday at 7 p.m. That is next Wednesday, February 8th at 7 p.m. And that will be on the end of chapter questions for chapter 17. So that means we are going to start chapter 17 today. Okay, and also our own work assignment will be posted today, and that will be the end of chapter questions in chapter 17. And that will be due on Thursday, February 9. Due on Thursday, February 9 at 11 p.m. Okay, so let us get the session going. Emma, could you go ahead and read for us what the topic for today is?
Chemistry of alcohols and phenols. Nomenclature, syntheses of alcohols, reactions, and synthetic strategies.
Okay, very good. Okay, just as Emma has read for us, we are going to start with chapter 17 today, which of course deals with the chemistry of alcohols and phenols. Okay, with particular attention to nomenclature, synthesis of alcohols, reactions of alcohols, and of course we are going to do a lot of synthetic strategy for this particular chapter. You will also notice that most of the reactions in this chapter we have done before. So this chapter will be mostly review chapter for all of us. Okay, at this point, let us look at the learning outcomes. Clear. Can you go ahead and read the first learning outcome for us? Okay, what does that mean? What does that tell you? That at the end of this chapter, you should be able to do what? Exactly. Okay. 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 I see some fly bugging everybody here. Okay. Okay. Jessica, go ahead and what is the second item on this learning outcomes? And what does that mean? That means at the end of this, at the completion of this chapter, you should be able to. Exactly. Okay. So anyway, you should use these all these items on this slide as a study guide. So at the end of this completion of this chapter, you should be able to do every single item on this list. Okay. So at this point, the question is still here. This is becoming a terrorist. Okay. Okay, let's leave the fly alone. Okay, it's just the fly wants to study some organic chemistry. So, so at this point, let us take a look at what are alcohols. I'm sure you've seen this before. This is, remember I told you before that most of this chapter is review. Okay, Brian, how many types of alcohol do we have? 3 types. Okay. How did you know that? Can you tell us the type of alcohol that we have? Okay. So in essence, we have 3 types of alcohols: primary alcohols, secondary alcohols, and tertiary alcohol. So if I give you this molecule here, what kind of alcohol is this? What kind of alcohol is that? Secondary alcohol. Very good. What if I give you this? Wow, this. If I give you this, okay, wow. If I give you this, what kind of alcohol is that? What kind of alcohol is that? Okay, for those listening to this lecture, we do have a trial just molesting everybody here. Because when you start listening to this lecture, you wonder why everybody's smiling and laughing. Okay, so what kind of alcohol is this? Primary alcohol, okay. Okay, everybody's here. What kind of alcohol is that? Tertiary alcohol. So in essence, you see here, alcohols are those organic molecules in which you have the hydroxy group. This is the hydroxy group. It's attached to an sp3 carbon atom. In other words, for a molecule to be an alcohol, the hydroxy group must be attached to an sp3 carbon atom. In this case, as you guys have rightly said, we have 3 types of alcohols: primary, secondary, and tertiary. Now, some other features of alcohols, if you look at an alcohol, you have, on the oxygen atom, you have 2 pairs of non-bonding electrons. These 2 pairs of non-bonding electrons are in sp3 hybridized orbital. Okay, therefore, the oxygen atom, what kind of hybridization do we have on oxygen? So this oxygen, therefore, is an sp3 hybridized atom. Now, if you take another look at the alcohol, it's almost as though it is a derivative of water. This is water molecule here. The alcohol is just as much a derivative of water, in which we have replaced the hydrogen in water, one of the hydrogen in water, with an alkyl group or with a carbon atom. Now, because of the non-bonding pair of electrons in alcohols, this non-bonding pair of electrons could act in 2 ways. It could act as a base. For example, if you have a proton This non-bonding pair of electrons could attack the proton in an acid-base reaction. This is acting as a base, and of course this is your acid to form there we see our one pair left. Now there will be a positive charge on the oxygen atom. Okay, this we call an oxonium ion. Just as we remember, when we see hydrogen, we have this here. When we have water, protonated water, we call protonated water hydronium ion. So the protonated alcohol is the oxonium ion. So a lot of reactions, therefore, of alcohols will involve the non-bonding pair of electron on oxygen acting as a base. Also, the non-bonding pair of electron on oxygen could also act as a nucleophile. It could act as a nucleophile in which anytime you have say for example you have this. Okay, because of the positive nature of this carbon here, remember that we could draw a resonance for this. Where this carbon becomes positively charged. Now this pair of non-bonding electrons on the oxygen of the alcohol could also attack any positively charged species. It does not have to be this molecule, but any species that is positively charged, or any species that could develop a positive charge, the pair of electrons could attack this. So we call this, at this point, it will be acting as a nucleophile. So as you can see here, whether we call a species a base or a nucleophile depends on what it does. If an electron-rich species attacks a proton or pulls a proton from a molecule, we say it is a base. In this case, it is acting as a base in this reaction. But if that electron-rich species attacks a positively charged carbon or a positively charged atom other than hydrogen, then we say it is a nucleophile. Okay, so we are going to see this we're going to hear this type of terminology all through this chapter, because this chapter involves a lot of chemical transformation. Okay, so now let us go back to our alcohol. So now we know the types of alcohol that we have: primary, secondary, and tertiary. We also have here, this chapter also deals with phenols. Phenols are those molecules in which you have the hydroxy group attached to a benzene molecule, a benzene type molecule. Okay? Anytime you have the hydroxy group attached to a benzene type molecule, we say that is a phenol. It just so happens that this particular molecule here, the name of this molecule is phenol. It is also the name of a class of compound called phenols. Okay? So this also we call a phenol. Another class of compound that is related to the alcohols and the phenol is the enol. For the enols, you must have an hydroxy group attached to a carbon-carbon double bond. Okay. Carbon-carbon double bond of an alkene. That is different from a carbon-carbon double bond of benzene now. Keep that in mind. Okay, so anytime you have an hydroxy group attached to a carbon-carbon double bond, we say this is an enol. The problem with enols is they are very unstable molecules. So therefore, what type of molecule would it be? What type of molecule would that be? That's an enol. Okay? See, what happens, the enol rearranges very easily to the corresponding ketone or aldehyde, and that is why they are unstable. This is enol. The enol, they rearrange very easily, in which you have the bond between oxygen and hydrogen will break to form a carbon-oxygen double bond, and this pi electron will come here. So now you have this intermediate here. Now this is negatively charged. Of course, you now have the proton here. And what happens, this proton and this here, the negative, the protonated molecule from the enol, we call this an enolate anion. We call this enolate. We refer to this as enolate. Okay, the enolate ion is that ion that you obtain, the anion that you obtain when you rearrange the enol so that the negative charge will be on the alpha carbon, and then what happens here, that enolate anion will simply pick up the proton, because the enolate anion here will be acting as a base. And then what do you have? You now have the ketone. So what you see here, the enol will rearrange very easily to the corresponding ketone or to the corresponding aldehyde. So we are going to be doing a lot of enol chemistry in subsequent chapters. Okay? Now let us now begin to look at the nomenclature of alcohols. So most of our time will be spent on the chemistry of alcohols in this chapter. Nomenclature of alcohols. Of course, the simplest alcohol is this molecule here. Which we call methanol. As you will observe here, the name methanol is of course derived from the corresponding name from the name of the corresponding alkane. The corresponding alkane will be CH4. It's only one carbon, meaning that that is, what will be the name of that molecule? Methane, right? So to obtain the name of the corresponding alcohol, we remove the E ending and we replace with OL. And that is how we got methanol. Okay, so what if we have this molecule here? What will be the name of that molecule? Ethanol, okay? And that is your drinking alcohol. I know you guys don't drink alcohol. Yes. Okay, that is your drinking alcohol, okay? By the way, this methanol here, this is poison. Okay, you don't even want to try that. That will make you blind if you drink it. Seriously, it is actually used to what they call detonator to poison industrial alcohol, so nobody will drink the industrial alcohol this year. Okay, supposing we have this molecule here. Okay, what would be the name of that alcohol? Propanol. Okay, now let us increase the complexity of this. Now you say this is propanol. Is that the only propanol we could get? What kind of other propanol can we get? We can get the isopropyl alcohol. Okay, so in other words, supposing the hydroxy group is on this carbon here, so what are we going to call this? That is the common name. That is isopropyl alcohol. By the way, that is the rubbing alcohol. You know, the alcohol that we use for rubbing your skin. That is isopropyl alcohol. That would be the common name. What would be the IUPAC name? What? Okay, the IUPAC name. Okay, with the IUPAC name, you look for the longest carbon chain, and you assign the carbon attached to the hydroxy group the lowest possible number. In this case, the name will be 2-propanol. This will be 2-propanol. Okay, given that scenario, what other constitutional isomers can we get from, no, not this one here. If I give you this, how many alcohol constitutional isomers could we get from this molecule here? How many? Okay, what is the name of this one? Okay, butanol. What kind of butanol? 1-butanol, exactly. Okay, 1-butanol. Keep in mind, you assign the carbon attached to the hydroxy group the lowest possible number. That is 1-butanol. Okay, so what other butanols can we obtain here? Okay, which will be constitutional isomers of 1-butanol. Okay, supposing we place the hydroxy group on this carbon here, right? So that becomes what? 2-butanol, right? Okay. Is that all? Is that the only constitutional isomers we can get from here? Okay, supposing we have this. Where? Okay. Rearrange the carbon skeleton, right? Okay, that molecule still has 4 carbon atoms, right? So it has the same formula as 1-butanol. So what are we going to call that? The IUPAC name for this? 2-methyl propanol. Now, there is another way we name alcohols. For example, we have 2-butanol here. The more recent recommendation, IUPAC recommendation for naming alcohols would be, instead of placing the 2 before the base name, you could have butyl, okay, and before before the suffix OL, you have 2, or butyl 2-or. Okay, so this molecule also could become 2-methyl. Instead of placing the 2 here, becomes propan 2-or. Okay. Now, if you have a cyclic alcohol, like this molecule here, you do not need to indicate the position of the hydroxy group. The position of the hydroxy group is assumed to be position number 1. So, okay, therefore this becomes what? Cyclohexanol. Now, supposing I have this, if I have this here, and I want to name this molecule as an alcohol, what would be the name? 3-bromo-cyclohexanol. Very good. Now, if I have this, I have an alcohol and I have an alkene, a carbon-carbon double bond. Okay, the alcohol would take preference. In other words, the position number 1 would be assigned to the alcohol in this particular case, and therefore the carbon you then indicate the position of the double bond. So in this case, this is position number 1, position number 2, number 3, number 4, number 5, number 6. So this becomes 2-cyclohexene. Remember the alkene is hexene, right? So remove the last E of the alkene name. I simply now replace with 2-cyclohexenol. Now, supposing we have this. Supposing we have this. Okay, how do we name this molecule? The first thing you need to ask yourself, which is the longest carbon chain that contains the hydroxy group? And where do you going to start numbering? You start numbering from here? Okay, so this is carbon number 1, number 2, 3, 4, 5, and 6. So the base name contains 6 carbon atoms, and we have a double bond in position number 4. Okay, so this becomes 2. I'm sorry. So this becomes 4 hexene. Okay, remember you remove the E, hexene 2 O. Okay, for this molecule here. The double bond is in position number 4, and the alcohol is in position number 2. Okay, so let us go back to, okay, so now let us go back to our slides. Okay, so you now see here, this name here, this molecule here, called 2-methyl-2-pentanol, based on our discussion so far, right? The longest carbon chain is 5, hydroxy is in position number 2, and methyl in position number 2. Okay, now if you want to use the new name, it becomes 2-methyl-pentene-2-ol. Okay, you could use either one of them. Okay, now supposing you have 2 hydroxy group on the same molecule. In this case, as you can see here, you have a cyclic molecule. At this point, we also need to bring in the stereochemistry. This hydroxy group and this hydroxy group, they are on the same side of the ring. So they become cis stereochemistry, and the relative position that you have those hydroxy groups, they are in 1,4 position. So we say 1,4 cyclohexane. Now this time you give the complete name of the corresponding alkane, and then of course because you have 2 hydroxy group, then you have the prefix diol. Now if you want to use this new name, you give the complete alkane name, then you give the position of the hydroxy group. In this case, 1,4-diol. Yes, right. Yes, yes. And okay, say for example, if you have this, what are we going to call that? What are we going to call that? They are in 1-3 position relative to each other, 1-3 position relative to each other. And what is the longest carbon chain? 3. So, and that becomes propane. So therefore it becomes 1-3 propane diol. Now if you have 3 hydroxy group, then it becomes triol, and you give the position of those hydroxy groups. Now if you take a look at this molecule here, in this case, this group here, this is the phenyl group. No, you leave that alone. No. Okay. Okay. This is phenyl group. Okay. This here. You should know that from the last chapter, chapter 15. So in this case, you use this phenyl group as a substituent. As you can see here, this becomes 3-phenyl, 2-butanol, because the longest carbon chain is 4, 1, 2, 3, 4, and the hydroxy group is in position number 2. Okay. Say that again. Yeah, go ahead.
I don't understand the whole thing.
You do? Okay. This group here is called a phenyl group. Just as we say this here, and we say this here is a methyl group, right?
Right.
That's it.
So is the benzene ring attached to that?
Yes, yeah. When the benzene ring, when you want to use the benzene as a substituent, that becomes a phenyl. Okay? You keep in mind that is the benzene without the hydrogen now. It is, you are attaching something to it, yes.
How come that group to the right is not the constituent with less than 6 carbons?
Oh, no. In this case, we are naming this, the alcohol, we're simply naming this as an alcohol. The alcohol takes preference. Okay. Not the alkane part. Okay. Okay. The question that Emma was asking, how come previously we said that if the group is less than 6 carbon atom, we name it as an aromatic molecule. But in this case, this molecule we are naming this as an alcohol. So we have to go by the alcohol guidance for naming this. Okay. So I'm going to leave the issue of nomenclature to you. As you can see here, this other nomenclature here, you should be able to do this. But before we leave this molecule here, anytime you have, I think we did that in the last chapter, the carbon that is attached to the benzene ring is called a benzylic carbon, and therefore this group here becomes a benzyl group. This group here is called a benzyl group, which you have benzene attached to a CH2, that's a benzyl group. And this carbon here is called a benzylic carbon. Okay, and the hydrogen attached to the benzylic carbon is referred to as benzylic hydrogen. As you see, and probably seen in the previous chapters, the benzylic carbon has a special reactivity that we are going to be discussing subsequently. Okay, now let us name this before we move to the synthesis and reactions of alcohols. Let us name this molecule here. Let's do this together. What would be the name of this molecule? What's the first thing you do? What is the first thing you do? Look for the longest carbon chain that contains The hydroxy group. Okay. So you have two hydroxy group here. So what is the longest carbon chain? Okay, this is 1, 2, 3, 4, 5. You could go here or you could go here. It doesn't really matter, right? 6. Okay. So now what do we name this? We have in the 5 position we have methyl group, right? So because 5 methyl. Okay. And then what? Okay, we want to go by the old name. That will become 2,4. Hexane diol. Okay. Now, if you want to go by the more current name, what will it be? 5-methyl hexane, right? 2,4 diol. Okay, very good. Okay, now let's name this. Let's name that molecule. What will be the name of this molecule? The longest carbon chain containing the hydroxy group. Starting from here. 1, 2, 3, 4, right? So that would be a butanol. Okay, so it becomes what? And we have the phenyl group is in what position? Is in position number 4. Okay, right here. So that becomes, what comes first, phenyl or methyl? Methyl, because of what? Alphabetized in order. Okay, so that becomes, I'm sorry. Two methyl, okay, 4 phenyl, what is butane or 2 butanol, right? Okay, 2 butanol. So I will leave the alternative name for you to give. Okay, about this molecule here, how will you name this molecule? Trans. Okay, very good. Okay, trans. You say trans. Okay, position number 1 is what? Hydroxy group. 1. Where's position number 2? 2, 3, 4, 5, right? So these are cyclopentanol, right? Okay, so that becomes, and the bromine and the hydroxy group are trans to each other, so that becomes trans 2-bromo cyclopentanol. Okay, very good. Okay, so at this point, everybody should be able to do the nomenclature. So, Jessica, have we accomplished the first 2 items on that, on the learning outcomes, right? Okay. So, as we say, at the end of this chapter, you should be able to name alcohols. So, I've done my part. It's left to you now, right? Okay, let us now go to reactions of alcohols. But before we do that, I want to show you this scheme here, just to give you an idea the centrality of alcohols in organic chemistry with regard to synthesis. Okay, from an alcohol, you could go to all these classes of compounds, And from these classes of compounds, you could make alcohols. Okay, so you see the centrality of alcohols here. For those of you going to the pharmacy school, who are going to be doing a PhD pharmacy, or those of you going to graduate school in chemistry, organic chemistry specifically, you're going to find alcohols are very, very important molecules indeed. And those of you who are going to the medical school, since you do not want to do too much work, you, you just want to make money. Yeah. And somebody asked me one day, he said, "What kind of doctor are you? The money doctor or the work doctor?" So anyway, you find that even though you may not use organic chemistry when you become a doctor, but before you become a doctor, you need organic chemistry in your biochemistry courses. So you need to take this very seriously. Okay. So this is just showing you the centrality of alcohol. So at the end of this chapter, we should be able to ask yourself, can I make an alcohol from ether, from aldehyde, from ketone, from alkene? All of those, some of those we've done before, from carboxylic acid, from ester, from alkyl halide. All of this you should be able to do. Okay, now let us now begin. What time is it? I see people parking there. Oh, we've got plenty of time. Okay. Just stop me 5 minutes to the end of class. Okay, now let us begin to take a look at the synthesis of alcohols. Have you seen this reaction before? So we don't need to discuss this anymore, right? Just move on. You want us to talk about it anyway, right? Okay, I'm sure you guys have seen so much of this. We could make alcohols from alkenes. Okay, as you can see here, carbon-carbon double bond. And what kind of reagent is this? Hydroboration reagent. In other words, what does it do? Exactly. It's an anti-Markovnikov addition of water across a carbon-carbon double bond. That is what this reagent does. It is also stereospecific. Stereospecific. What do we mean by that? We mean that it only gives one type of stereoisomer. In this case, we're going to get the cis isomer. In other words, this is a syn reagent, what we call a syn reagent. It will add the element of water, which is in this case hydrogen and hydroxy group, across the carbon-carbon double bond on the same side of the molecule. And that is why we call this a syn reagent, in other words, or cis reagent. Okay? So it is stereospecific. We will form only one particular stereoisomer. That we know. And it's also anti-Markovnikov addition. Now, what do we mean by anti-Markovnikov addition? Okay, hydrogen goes to the carbon that has less hydrogen. Okay? The hydrogen goes to the carbon that has less hydrogen. That is anti-Markovnikov addition. Okay, so we therefore call this also a regiospecific reaction because the hydrogen goes to a particular carbon atom. We call this also regiospecific. Okay. Now another way in which to make an alcohol from an alkene that we've done before, we take mercury acetate followed by sodium borohydride. Okay, what does that do? It is a Markovnikov addition of water. We say the borane is this is anti-Markovnikov. That is anti. But we say this is Markovnikov. In other words, what does that mean? this reagent here. What does it do? It adds water across the carbon-carbon double bond so that the hydrogen goes to the carbon that contains more hydrogen. Okay? In the Markovnikov addition, the hydrogen goes to the carbon that contains more hydrogen. Okay? And that is why you get this product here. Okay. So we know that already. Okay, we've seen this also. I told you most of the reactions here we've seen before. Okay, this is osmium tetroxide followed by sodium hydrogen sulfide. What does that reagent do? Exactly, it's a syn addition reagent. Syn addition reagent. In which case, the two hydroxy groups are added across the carbon-carbon double bond in such a way that those two hydroxy groups will be added on the same side of the molecule. Okay, so you see this hydroxy group and this hydroxy group are cis to each other. Okay, so this is also a stereo-specific reaction. Now, if on the other hand, you want to add two hydroxy groups across the carbon-carbon double bond, so that the two hydroxy groups will be opposite to each other, will be trans to each other, then you want to use this reagent. You already know that. Okay, so this here we use a par acid, called par acid. And par acid at this type of molecule, keep in mind that is a carboxylic acid, right? Everybody knows that? That is a carboxylic acid. Now, for a par acid, what you have is this here. Instead of this oxygen being bonded to hydrogen, it is bonded to another oxygen. Okay, so that is why we refer to this as a par acid, somewhat like peroxide acid. It's very similar to hydrogen peroxide. This is hydrogen peroxide, right here. Okay, you have oxygen-oxygen bond. That's a peroxide. When we say peroxide, we mean that we have oxygen-oxygen bond. And so therefore, whenever you have this, we call this a par acid, almost like a peroxide acid, and then we abbreviate as RCO3H. So anytime you take a par acid and you have a carbon-carbon double bond, see what that is, go to a blank page. If I have this, a carbon-carbon double bond. If I take a par acid, for example, par-benzoic acid, keep in mind it is CO3 with hydrogen, par-benzoic acid, the first thing that happens, what is the first thing that happens? We should know that by now. What is the first thing that happens? What is it? It forms a peroxide. I'm sorry, it forms an epoxide, okay? It forms an epoxide. So the reaction of a par acid with a carbon-carbon double bond is an epoxide. Okay? And that epoxide, once you add dilute acid to it, hydronium ion in this case, it will open up the epoxide in such a way that the two hydroxides that will be formed will be trans to each other. Okay? And that is what this reagent does. So that is why very often you will see us, if I have this, you simply have the fat acid. Let's use a generic fat acid, step 1. You do not add both together, okay? Because the epoxide has got to be formed before you add the acid. Then step 2, you add the acid. And then that will give you your product. And this process, or the process of adding 2 hydroxy group across a carbon-carbon double bond, is referred to as hydroxylation. Hydroxylation. Okay? So let us go back. Okay, so therefore you see here, okay, so you have the carbon-carbon double bond, the fat acid followed by hydronium ion or any kind of acid, you form your diol. Okay. Now, this is a new set of reactions. We have not done this before. Okay, so I will take a little time on this. We could also convert an aldehyde to alcohol using this reagent here. I will give you the reaction mechanism later, but let's just focus on the product for now. Anytime you take an aldehyde and you take this molecule here, we call the sodium borohydride. Sodium borohydride. Okay. Anytime you take sodium borohydride and you have an aldehyde, and then you follow that up with an hydronium ion, you get a primary alcohol. Keep that in mind. You get a primary alcohol. If, on the other hand, you take a ketone and you use the same reagent, by the way, the ethanol here is just acting as a solvent. Okay. You take a ketone with the same reagent, you get a secondary alcohol. Okay, here, from aldehyde you get a primary alcohol. From ketone you get a secondary alcohol. So if you want to make a secondary alcohol, you take a ketone, you react with sodium borohydride, and you get your product. Now another reagent which is similar to sodium borohydride is lithium aluminum hydride. That would do the same thing. Lithium aluminum hydride. Very often we simply refer to this as LAH, acronym LAH, lithium aluminum hydride. The lithium aluminum hydride will do the same thing as sodium borohydride. In other words, it will take an aldehyde and transform to a primary alcohol after you add the hydronium ion. It will also take a ketone and transform to what? A secondary alcohol. Okay. Now, the lithium aluminum hydride, however, does something else that the sodium borohydride cannot do. The lithium aluminum hydride will take a carboxylic acid and convert the carboxylic acid to a primary alcohol. Sodium borohydride cannot do that. Huh? Say that again. What? Oh, what does it do? The lithium aluminum hydride will convert a carboxyl group, this here, to a primary alcohol. But sodium borohydride will not do that. Okay? So what you do as a research chemist, you're looking for reagent that will do specific, that will perform specific functions. So when you are making drug, you may want to introduce a particular function in this molecule, and then you want to use a particular reagent to do that. And so people make careers out of developing reagents. So we have more work for you guys to do at the undergraduate level, right? Okay, so therefore, what you have here, lithium aluminum hydride will convert a carboxylic acid to a primary alcohol. It will also convert an ester to a primary alcohol. And sodium borohydride cannot do that. Okay? Yes.
First molecule is really big. Does it matter? We have like 7 carbon chains.
Does it have 7?
I'm saying, does it matter that big that has a double bond, or is that just...
No, it doesn't matter. No, the lithium aluminum hydride will not do anything to the double bond. That's fine. It does. See, most of the reaction that we deal with in organic chemistry, it does not matter how big the molecule is. You focus on the functional group. Okay, your focus should be on the functional group. Okay, given that, before we leave this section, how can you make this compound, this transformation? Let us do this together. I want you to go from here to here, okay? I want you to go from here to here. What exactly do we need to do at this point? If that is the problem that you have to deal with. Okay, where do we start? Okay, let us see. Okay, let me take. You want us to take. Oh, let me go here. Na. B. Okay, very good. So you need sodium borohydride. Why sodium borohydride? Excellent. Because the analysis that you guys have done, you see that all we're doing here, we want to transform the carbonyl to the secondary alcohol. And we want to leave the ester intact, right? And the only way to do that is to use sodium borohydride. Very good. So those are the kind of thinking that you should bring to take. Because if you use, let me finish this. Okay, well, that will simply just give you this here. Because if you use lithium aluminum hydride, what do you expect to get? If we use lithium aluminum hydride, what do you get? Okay. Both of the carbonyl will be reduced to an alcohol, and the ester will be a primary, exactly. In that case, you will get this product here. One, two, three. And then this carbon becomes the primary carbon. If you use lithium aluminum hydride, that will be the product that you obtain. Okay, so very good. So you guys are getting the idea. So let's see how much time do we have left. Oh yeah, we still got plenty of time. Okay, this problem here, we will do this problem. We don't have enough information to do this right now. We will come back to do this. Oh, I did promise you I was going to give you the mechanism, right? Okay. No, let's do it now before we go to something else. Okay. Okay, let us now go to the mechanism of, because the reason I want to give you the mechanism, you'll find that that same mechanism runs through most of what we are going to be dealing with in the course of this chapter. Mechanism of, we call them metal hydride. Reduction of carbonyl compounds. Okay, let's start with the aldehyde. Say we have this aldehyde here. I'm going to use an R group here for a generic molecule. The sodium borohydride, think of the sodium borohydride and also the aluminum, lithium aluminum hydride. Think of it this way. You have boron attached to 4 hydrogen. Because boron here is, the valence of boron is 3, of course it needs 3 bonds, but it now has 4, so it is negatively charged. Okay? So the sodium is just there to counter the negatively charged borate ion. Now what I want you to do, think of each one of those hydrogen attached to boron, think of it as an hydride, as this here, hydride, negatively charged hydrogen ion. Whether it is aluminum, the lithium aluminum hydride or sodium borohydride, think of each one of them as an hydride, source of hydride. That's all. If that is the case, this hydride therefore could act as a base. Remember what we told you as a base? It could also do what? Act as a nucleophile. Okay? It could do both. So in this case, it will act as a nucleophile. So therefore, the mechanism we are going to give you here, simply just have the hydride here, attacking the carbonyl, because the carbonyl has a measure of positive character to it. The carbonyl carbon is electrophilic, looking for electrons. And notice when you draw mechanism, see my arrow. Okay, you always draw your arrow from the nucleophile to the electrophile. In other words, from where you have electron to where there is positive charge. Okay, the last thing organic chemists want you to do is to draw your arrow from a positive charge to a negative charge. I said, no, you're going to get, nobody will give you an A if you do that. Seriously, because that is the tenet of organic chemistry. If you draw at the end of this semester, I see an arrow from a positive charge to a negative charge. If you are going to be getting an A, I will have to shake my head. Oh my God, what did I do wrong? Okay, I did not train this person right. So you don't do that. Electron arrows go from negative charge to positive charge. Okay. So now you have the hydride goes to here. So that means you have this intermediate. Now this mechanism I'm giving you here also applies to the ketone or the ester. hydrogen is here. Now at this point, let us use a red pen to show this is the new hydride coming in. So that is this here. Okay, so now you form the alkoxide anion. You see why we add the water at the end or the acid at the end? So now at the end, you add hydronium ion. Okay, now this simply now picks up the proton, the intermediate alkoxide that you form, okay, or the oxonium ion that you form, will simply come here, act as a base, pick up the proton, okay, and that is how you form your product. That's simple. Okay, this is the hydrogen from the sodium borohydride, and that is how you form your alcohol. So the first thing that happens, the hydride will add to the carbon-oxygen double bond, and then the intermediate oxonium ion that you form will now be protonated by the hydronium ion. That is why we have step 1 and then step 2. You do not add those together. Okay, so what would be the mechanism for this? At this point, you should be able to give me the mechanism for okay, can you give me a mechanism for this here? Ketone to alcohol, secondary alcohol. What would be the mechanism? Okay, given that you have an hydride, what is the first step? Okay, attack the carbon. It's the same thing that we did for the aldehyde. No difference. And then you form the oxonium ion or alkoxide ion. And then what happens after that? You just add the acid. The acid will protonate the oxonium ion. That's simple. Okay, now what I want you to do now, when you go home, write the mechanism for the conversion of an ester to a primary alcohol. Seriously, do that. Write the mechanism for the conversion of an ester to a primary alcohol when you go home. I will give you a hint. The first, you're going to get an intermediate, okay? Which will be, that intermediate you're going to get will be an aldehyde. And then from aldehyde you go to the primary alcohol. Is it time?
Yeah.
Oh, okay. 5 minutes to the end of class, so just wait, let me give you back your exams. In the meantime, let me simply close this here. So I will see you guys on Tuesday, and on Tuesday we are going to finish chapter 17 on Tuesday.